Right, so we're on page 9. And I'll look at page 9. And we've got the heading Spontaneous Decay. Our booklet says on Earth the 3 major forms of radiation that we encounter are alpha decay, beta decay, and gamma emission. And this is true, but this is not all of the radiation that is emitted. These are just the main ones, and they're the only ones that we consider on this side. So we did think about what spontaneous meant before, and we also discussed what decay meant. Do you remember what that was? What was, yeah?
It's when the nucleus releases particles, something like that.
Yeah, yep, so it is from the nucleus. It's got nothing to do with the electrons orbiting the nucleus. But what's spontaneous? You see me?
It just happens abruptly. You can't predict it, you can't force it.
Yeah, so it's happening by itself, really. Can't force it to happen. And we also don't know when any particular unstable nucleus is going to decay. So we can get we can predict for a lot of atoms. If we've got a lot of them, we can see what the likely decay is. But for each individual, we cannot predict. And yes, we have our 3 main types, alpha, beta, and gamma, chosen as Greek letters. So because they're Greek letters, we can also write alpha as the Greek letter alpha, and beta is the Greek letter beta, and gamma is sort of, I do it like an upside down fish. But yeah, you can see how the font has a nicer looking gamma than I have. But if we think about, well, what are they made of then? What is an alpha particle? And it is a particle. It is a helium nucleus. And if I were to use that AZ notation to represent this helium nucleus, remember that on the bottom is the charge. And so a helium nucleus has 2 protons and no electrons. Right, so, and he's got a charge of 2. Its symbol is He, and it's also got 2 neutrons. So 2 protons and 2 neutrons gives it a mass of 4. So this is the more common way that we would represent it when we're writing out a nuclear equation, because it's going to help us count. Okay, this way doesn't really help us in our counting at all. A beta particle is an electron. Okay, and remember, it's from the nucleus. And the nucleus is ejecting an electron. And how are we going to write that in AZ notation? Well, we can either use a little lowercase e for an electron, or we could use the beta symbol. Well, what's the charge going to be? -1. And what's the mass? 0. Okay, so writing it this way helps us balance our equations. And then, so these two are actually particles. Gamma is just energy. Say just, but it doesn't have a particle. So if I'm going to write gamma, and its energy, it has no charge and no mass. And if you refer to the table that's in your booklets, you can see there that the mass of the alpha particle is given as 4. Well, that makes sense because we put the mass up here on our AZ notation as 4. The charge of +2, again, that makes sense because we've got a 2 down here and it's a positive number. If you look at the speed this particle travels at 5% the speed of light. That's slow for a nuclear particle. So slow, 5% speed of light. It's like a medicine ball, large and quite heavy. Its range in air, 4 centimetres. It can't go very far, and in fact, most times it's going to penetrate even less than that. Okay, so 4 centimetres in air. And it is stopped by skin and paper. So it can't penetrate the outside of your body. Okay, if there was alpha radiation around, it will be stopped by your skin or your clothing. That is a good thing in one sense, but it can also be a bad thing in another. In what way could it be bad? This +2 charge means that it is highly ionizing and it will burn your skin. Okay, it's going to give you a very nasty burn if it's in contact with your skin. Or if you happen to swallow it, then it will burn the inside of you, your intestinal tract. Our next particle, the electron, is much lower mass, and it is 90% speed of light. So it is quite fast. Its range in air, about 1 metre. Much harder to stop. Stopped by 2 millimetre thick sheet aluminium. Okay, so able to go 1 metre, but if we wanted to stop it sooner than that, then we would need to have a barrier. It's also about the thickness of your hand, its penetrative properties. So if we have a beta source on the palm side of your hand, you would be able to detect some of it on the other side of your hand. But if you had the source on one side of your arm, you wouldn't be able to detect any of it penetrating through to the other side of your arm. Okay, so that's about the limit of its penetrating ability through humans. Gamma travels at the speed of light. So it's very fast. Its range in air, 100 metres. So it can, because it's a wave, it's able to have a high range, and it's very difficult to stop. 2 centimetres thickness of lead or 2 metres of concrete to stop gamma. So it is much more, it has a very high penetrative ability. Yeah?
How is like an electron like booted from the nucleus if it's in shells?
Well, this we'll get to that in a moment, I guess. We definitely will. It's not coming from the electrons, but if we think ahead, and I'll show you this in a moment, what happens if a neutron ejects an electron? It becomes a proton. And that's what happens.